I kind of saw this problem online and I'm going to make up my own version. So the problem online said, here's some string and it can support some maximum tension, and then here's a mass. And the question was, would it break if I hold it up here and let it swing down? My version says, here's the maximum tension in the string. What's the biggest mass I can put on the end of the string so that it doesn't break when it swings down the bottom? And then I'll do a bonus problem after that. So let's get started. Here's my diagram. So I have a mass up here. I'll stand right here. I have a mass up here on a string of length r, and then it swings down here. Let's say I picked the maximum tension was 20 newtons, and the radius of the swing, the string was a half a meter. So let's just start at the bottom. Okay. So at the bottom, it's going to have some velocity. I'm actually going to call that v2, and we'll see why in just a little bit. And I want to draw the force diagram for that. At the bottom, we have this. There's my mass. I have the downward gravitational force mg. The string pulls up with the tension T. Okay, and you'll notice that I drew the tension greater than the gravitational force because at this point, the ball is moving in a circle. So if I call this the y direction, I can say F net y, and the y component of forces is going to be equal to the tension minus the weight, and that would be equal to m v2 squared over r. So it's moving in a circle, so it's going to have centripetal acceleration. Remember, the centripetal acceleration is v squared over r towards the center of the circle. So it's accelerating up, and if it's accelerating up, then the tension has to be greater than the weight. And so that's true. Okay. So I can solve for the tension. T equals mg plus mv2 squared over r. But I don't know how fast it's going. So now I need to go back and do a different problem to find out how fast it's going. So let's write this little result over here. T equals mg plus mv2 squared over r. Now, if I just find my v2, then I'll be all set. Okay. Now, if you wanted to try to use something interesting like Newton's second law to find the speed at the bottom, good luck with that. Because just imagine, as this thing's moving down, the gravitational force is down, the tension changes direction. And so since the tension changes both magnitude and direction, it's a non-trivial problem. It really is, right? Because this tension applies the force to constrain the motion in the circle so it can change and be whatever it wants up to the maximum value. So finding the component of gravitational force in the direction of motion is not trivial. But we can use the work energy principle. So remember, the work energy principle says the work is the change in energy. And if I pick a system and spell it correctly, of the ball, I'm calling it a ball plus the earth, then I can have two types of energy. I can have kinetic energy, 1/2 mv squared, and I can have gravitational potential energy, mgy. And so in this case, for the gravitational potential energy, I get to pick where y is equal to 0. Just to make things easier, I'm going to pick down here as y equals 0. Well, is there any work done on the system? Remember, work is F delta R cosine theta. So this is the force that could do work. That's the displacement. And theta is an angle between the way the force is pointing and the displacement is. So I did not include the string as part of the system. So could it do work? And the answer is no. Because the tension is this way and delta R is that way. The tension is always perpendicular to the direction of motion. So cosine of 90 is 0. No work done. That's good. So now I can call this position 1, this position 2, like I said. And I have work as 0, which is the change in kinetic energy, plus the change in potential energy. And I want to point out a lot of times, I get students just saying, the energy here is equal to the energy there. And it's not completely wrong. It's just kind of a bad idea, right? because that skips the step of saying, well, that's only true because the work is zero. So if you don't say work energy principle, if you don't declare your system, then that may or may not be true. So you want to do it, I think you want to do it this way. And it's just full and complete. So next, I can start canceling some stuff. So that's my kinetic energy at the end. That's my kinetic energy at the beginning, up here. So if I release it from rest, then this is 0. Also, here, y is equal to 0. So y2 is equal to 0, so the potential energy down there is 0. That's only because of where I picked my y. Okay. So putting in my values, I get 0 is 1/2 m v2 squared, that's my final kinetic energy, 0, 0, minus mg, and then my initial height above here is r. Now I could solve for v2, but I'm just going to solve for v2 squared. v2 squared equals, let's just put it all together, 1/2 m v2 squared equals mgr. Mass cancels, multiply by 2. v2 squared, that's a 2, is 2gr. Okay, it has the right units, meters per second squared times meters squared per second squared. Now, see, I didn't need to find v because over here I had a v squared already. So I'm just going to take that expression for v squared and plug it in over here. And I get t equals mg plus m v squared, which is going to be 2gr, over r. So I get mgr plus 2 mgr, 3 mg. So the tension at the bottom is going to be 3 times the mass of the thing. That's kind of interesting, really. Notice that it does not depend on the radius of the circle. It did depend on where it started, and we'll do a slightly different problem in just a second. And now let's just go ahead and find out the maximum mass. I said that what that was. Let's say the tension is, maximum tension is 20. So I say 20 equals 3 times mg, m max is going to be 20 divided by 3 times 9.8. Let's just put it in the calculator. Everybody loves numbers. Everybody loves numbers. I know that. So 20, enter, 3 divided by, 9.8 divided by. And I get 2.04 kilograms. Okay. So that's the maximum mass you could have. Any mass greater than that, the tension is going to be greater than the breaking tension of the string. Cool? Cool. Now, it does depend on what planet you're on, right? G is still in there because you know, imagine being on a very, very low mass planet, then you could obviously increase the mass of that. It doesn't depend on the, I mean, it's proportional to the weight, but it's not, it does depend on G. Okay, now let's look at the next question. Suppose I pick a mass of 4 kilograms. Well, let's see, 4 times 9.8, that would be too much, right? If I double, no, it should be fine. 4 times 9.8, wait. 20 newtons, that's, I did that wrong, I have to be wrong. 20, 3 divided by, 9.8 divided by, yeah, okay. You should have caught me. Okay, 0.68 kilograms. So let's pick 1 kilogram. What if I pick a mass of 1 kilogram? Well, if I release it from up here, it's going to break. So what angle could I release it from and not break? And you'll notice, see what I did in my head there. I said, okay, the weight has to be less than 20 newtons. Otherwise, it would break just hanging there. Okay. So we want to change the problem up. Let's just erase this whole thing. This is still true, right? So I'm not going to erase that. Let's just draw a different diagram. The tension as related to velocity is still true. So, but now I'm doing this. I'm going to release it from some angle theta. Let's go back to the work energy principle. This is all still true. true, 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 not true, right? The only difference is that if I release it from some position right here, its height above the final point is not r. That's the only difference, okay? So all I need to do is define that. So let's erase that. If this is a length of r, that's a length of r. This whole thing is r. This part right here is going to be r cosine theta. So that means this part right here is going to be r minus r cosine theta. So that's my initial height, r times r minus cosine theta. So all I have to do is put that in right there. And let's just erase some stuff. One minus cosine theta. And in this case, remember, I'm solving for theta. Okay, so I have 0, the mass cancels. So I'm going to add that to the other side, and I get 1/2 v2 squared. But v2, I lost it. Oh, I'm trying to solve for v2. And then I'm going to put, yeah, let's just solve this for v2 squared. That's what I was doing. Okay, so I get, move this to the other side and multiply by 2, and I get 2gr 1 minus cosine theta. Now I can put it in my tension equation over here. I know the maximum tension. I'm trying to solve for the angle theta. So let's put that in. I get T equals mg plus m v2 squared, which is this, 2gr 1 minus cosine theta over r. Those cancel. If I want to solve for cosine theta, okay, I know my tension max, so let's just subtract this. I'm going to erase all this stuff. I like to keep a track of what I did, but in this case, I'm just running out of room. T minus mg equals m 2mg times 1 minus cosine theta. Now I'm going to divide both sides by 2mg. T minus mg over 2mg equals 1 minus cosine theta. And now I'm going to add that to both sides, subtract that from both sides, and I get cosine theta is equal to 1 minus T minus mg over 2mg. And so now I can solve for theta. Theta is going to be the inverse cosine of 1 minus the max tension, which was 20, minus 1 times 9.8, so it's just 9.8. I'm putting in my numbers. Over 2 times 1 times 9.8. Okay, let's put it in our calculator and find out what happens here. I'm kind of curious. So 1, enter. 20, enter. 9.8 minus 2 divided by 9.8 divided by, now that's that whole number, and then I'm going to subtract that from 1, and then I'm going to take the inverse cosine. I get 61.3 degrees. So I can pull it back to an angle of 61.3 degrees. When it gets down to the bottom, the tension would be exactly the maximum tension for a 1 kilogram mass. If I went higher than that, then the tension would be greater and it would break. Kind of a fun problem. I had fun. I hope you had fun too.